All right, we're going to take a look at electric fields. In Physics 111 or any mechanics class, you should have studied forces extensively, and we looked at electrostatic forces last week as well. Electric fields are related to electric forces, but it only requires that source charge to produce as opposed to two objects applying a force on each other. So all objects produce an electric field that permeates space. That just means it goes through space, all right? And so anytime we're talking about this, we're usually talking about charges that are in air or a vacuum of space, as opposed to something else that would prevent the electric field from permeating around, all right? And so right here, this is a point charge. This is what we're going to be focusing on this week. We will also get into charged parallel plates, and that's where we look at our capacitors, where we have a positive and negative charge to our plate. We can do all kinds of different shapes like cylinders and cubes and all kinds of things, but in this course we're going to focus really primarily on a point charge, and then when we have multiple point charges, what happens when we have both of those together, okay? So when we think of an electric field, it's easy to think about or to relate it to gravity, because that's something that we know and understand, right? So if you think about a gravitational force, all right, we also have an electric force. So gravitational force is between two objects in space, like the Earth and the Moon, or us and the Earth. And then just like an electrostatic force that we did last week, you have a force between two charges. Now, an electric field is there. So if you think about the Earth's gravitational field, right? So the Earth is hanging out in space, and it's got a gravitational field all around it that is pulling things towards it. So that's how we get things like meteorites that come into our atmosphere, because they got close enough that the force was being able to apply on that meteorite. All right, but if that meteorite is coming in here, and then it's going to kind of be pulled in. All right, but if that's not there at all, this gravitational field is still present, okay? And so that gravitational field is there regardless whether it is acting upon anything. All right, so similarly, if we look at this point charge here, that little positive point charge has an electric field around it regardless of anything else. So it's independent of any other charge. As opposed to what we looked at last week, you would have two charges and then a force between them. So that's where you had Q1 and Q2. All right. And so we're going to be taking a look at that field. That field obviously goes, it changes with distance. So our electric field is defined by the electric force per unit charge. All right, so it is the amount of force it is going to apply per charge. Just like our gravitational field is the amount of force per mass, meaning that if a little small asteroid came into region, it would be pulled in, actually not an asteroid, but a meteor. It would be pulled into our atmosphere, as opposed to maybe a larger piece wouldn't have quite as much force on it, and so it wouldn't be able to actually be pulled in. And so that amount of charge, it's going to be the force applied to the amount of charge, okay? And so the direction of the field is the direction the force would be applied if it was a positive. All right, so last week we looked at this too. We looked at our electric field lines. So anytime we have field lines going out of the object or the charge, it is positive. And if it's going in towards the charge, then it is negative. That should be a review from last week. All right, so here is our source charge. So this capital Q here, that is a positive source charge. So you can see that the forces being applied is going outward. All right. If we had a little test charge right here, that's the direction it would go. All right, but this field is there regardless of that test charge. So even if we took that test charge away, that field is going to be there. All right, so what we're going to do this week is be able to calculate the force that would be applied, or the strength of the field at any given distance, or the force being applied at that specific distance or for that specific charge. And so Our electric force is a physical force that exerts on one another. So anytime we have, this is just the difference between force versus field. Anytime we have a force, okay, if you think of Newton's third law, and this is the one everybody knows but doesn't really understand, that there's an action and reaction. For every action, there's an equal and opposite reaction. Okay, if I hit the table with my hand, like if I get mad and I punch the table, it's going to hurt my hand too, right? Because the table technically punched me back. So in order for me to exert a force, I actually have to have contact, and it has to actually have two objects. I can't just be sitting here applying a force to the left, right? I actually have to physically push something to the left. However, these fields are there regardless, all right? So it's a potential force that could exist. So if you take this positive charge here, all right, that field is existing regardless of anything else coming into contact or coming near it. But at this point in time, it is not exerting a force on anything because there's nothing there to exert on. All right, but then if I take a little negative charge and add it right there, so now this positive charge is going to apply a force on this negative charge, okay? So this positive here, I like to use a capital Q to show that it is the source charge. It's the one providing the field, just like the Earth is providing that gravitational field, all right? And then I like to use a lowercase q for the test charge. That's what's being affected by the field, okay? That's like your little like the satellites around the Earth or the moon or things like that. That is what is being affected by the field. It's typically smaller than the source. The source is typically the bigger of the charges. So when we said that the electric field is defined by the electric force per unit charge, okay, its symbol is a capital E, and then our units is newtons per coulomb because it is a force per charge, which means if we were to write an equation of this, my electric field is going to equal my force per charge. All right, so that is your next equation here. You will be creating your own equation sheet, so if you haven't started already, please make a list of equations and constants. It'll help you in the end in order to make your equation sheet for our final exam. Okay, so our electric field is equal to the force divided by our charge. Now, that is great when we know that little test charge, right? If we go back here, if we know we already have a little test charge, that little q is what's in that equation, all right? But we don't always have that. And so if we take that out, we only have our source charge. Okay, but we don't know any more information, and so this equation becomes a little difficult because we don't know what that little q is. It could be anything, all right, but we don't actually have a value for that, so that equation's not going to be as helpful right now. All right, but, so I'm going to derive this for you. If we remember that our electrostatic force is K Q1 Q2 over R squared, right? That is our force. And we know that our electric field is equal to our force per test charge. Okay, so what I'm going to do now then is for this F here, okay, these are the same F, so I'm going to substitute this into here. All right, so we're going to have E is equal to K Q1 Q2 over R squared, and that's divided by Q. I'm going to call that Q2, and I'm going to pretend that Q1 is the source charge. Okay, so notice that Q2 is canceled out. So that little test charge is no longer going to be there. And we're left with our next equation, which is E is equal to K. I'm going to use a capital Q to show that it's the source. So that's the larger one providing that electric field, divided by R squared. All right. So that is equation number 2 for the week. That one is dealing with our source charge versus this one is dealing with the little test charge. So if we already know the force or we're asking for the force, given a field and a test charge, we can use this one. If we don't know anything about the force and we don't know anything about the test charge, then we know this one because we can say this source is providing an electric field at this distance. So this is it written kind of in the same, well, they're the same equations, they're just written a little differently. And so we know we have our electrostatic force, so that we had that last week. We can find the electric field strength based on the force applied and the test charge, or we can find the electric field strength of the source charge at any given point around that source charge, right? Because if I have a source charge here, it's going to go in all directions. And so if I say, well, what's the field strength at 5 centimeters? Well, 5 centimeters could be in any direction all the way around here. All right, so that's, again, similar to last week, why we call it a radius. So we have some electric field calculation practices here. I'm going to walk you through one or two, and then you could use these as guides in order to help practice these questions before you go do your calculation questions. All right, so a charge of 0.5 millicoulombs was placed in an electric field. The electric field strength at that point was 130 newtons per coulomb. What is the size of the force on that charge? Okay, so now because we're picking from equations, and we've got a lot of stuff going on here, I highly recommend you write out your given information. It's not required, but it is encouraged, especially if you are stuck in a problem. So in this case, I'm given a charge was placed in a field. So that tells me that that is my test charge, and that's going to be 0.5 millicoulombs. Now, we can't deal with millis, so we need to do our metric conversions. If you saw my metric conversions at in the physics resource folder, you could take a look there. But okay, that is a 10 to the negative 3. So instead of being a 0.5 millicoulombs, it's going to be a 0.5 times 10 to the negative 3 coulombs. Okay, so that is my charge. And then it was giving me a field strength, okay, of 130 newtons per coulomb. All right, and that's why it's important to know your units, so I know that this is an electric field strength. All right, so then I know E is equal to my F divided by Q. I can rearrange that, so my my F is E times Q. Now, if you like to rearrange them before adding in numbers, please do so. If you want to add in numbers and then solve for the unknown, that's up to you. You should have done enough math in your life to figure out what you like to do better. I'm not going to force you one way or the other. And then we plug in our numbers. Our electric field is 130, and then our Q is going to be 0.5 times 10 to the negative 3, which gives us 6.5 times 10 to the negative 2 newtons. All right, and that is your answer there. On this next slide, I have it written out for you, so you can see how it works there. Okay. So this one here, similarly, it's giving you some information here. Right now it's asking what is the electric field. So we're trying to solve for E. So that we're trying to look for, and it's giving us a distance from the center. All right, so my radius is 30 centimeters. Now we don't like dealing with centimeters. So again, our metric conversions, if you think about centi, okay, if you think about cents, how many cents are in $1? 100. How many centimeters are in a meter? 100. So if I told you I had 30 cents, right, you would also write that as $0.3, right? And so 30 centimeters is 0.3 meters. All right, so nice easy metric conversions there for you. And then we're given a source charge of 5.0 times 10 to the negative 9 coulombs. All right, so now we're going to plug that in to our equation. So because we have a radius and a source charge, that means I can use this equation here. And there's a few things to remember about this. All right, first of all, this is 8.99 times 10 to the 9. This here is 5 times 10 to the negative 9. And then we're going to divide that by our radius, which is 0.3 squared. Okay, now when you're doing this in a calculator, and I know some people had some issues with our scientific calculator in Lockdown browser, so if you have like a TI-84 or whatever, that's really convenient to use. I discourage Desmos. You can't be on another thing, and I don't want you on another device or phone or anything using it, and you're not allowed to use it on the final, so get used to using a regular calculator. But when you plug this in, I always like to put extra parentheses around this, so if you do this times this divided by 0.3 squared, if you don't put parentheses around the squared here, it's actually going to square your whole number instead of just that one. So please be careful with your order of operations. That's one problem that Desmos kind of thinks for you. And so you need to be able to think for yourself in order to figure these ones out here. All right. And so then our electric field ends up being, I got 499 newtons per coulomb for that answer there. Okay. So there's a few more practice questions in here. Please spend some time to go through them so you fully understand the calculations. All right, and this one is giving you a couple of steps there to do that one. Okay, so now we're going to talk about superposition. Oh, that looks kind of funny, sorry. Superposition is just a fancy word of saying when there's multiple things at once. All right, and so every charge in space creates an electric field independent of the other fields. All right, the result is the sum of those fields. Okay, so what that means is if I have a positive here and a negative here, okay, if the other one didn't exist, it would produce the same field strength on its own. But because they're together, we're going to add those up. So if I were to place a little sensor right here, in order to determine that field strength, I would have to take into consideration that this blue one field is going in that direction and this red one is going in this direction. All right, and so those two fields are actually working together, and if they're both the same charge, equal and opposite, you would have double the field strength right there as opposed to just having one charge on its own. Similarly, if I have a positive and a positive right there, this one is going in this direction and this one is going in this direction. All right, and so if those are both equal and opposite, then if I put a field sensor right here, okay, it would actually end up being 0 because they're canceling them out. All right, so these are vectors, which means we have to pay attention to the direction. It's like having 100 newtons of applied force and 100 newtons of frictional force. Those two forces are gonna cancel each other out. All right, so there's no change in motion. Our fields are the same way. We can have these fields and we can determine based on their directions. So this is an example from your lab that you're gonna do this week. So this yellow, it took me a minute to find that yellow dot. I'll make it nice and big. Okay, so that yellow dot is at the 60 centimeter position. And then we've got two electric fields. All right, so a negative here, this field strength is going to be going in this direction, right? Because negatives always go towards this, or towards themselves, as opposed to positives are away. So this one is going to be going away. All right, so those two are opposites of each other. So if I was determining the electric field strength right here at this position, I can tell that this one is going, the negative is going to the left and the red one is going to the right. And so I would actually subtract those because those are going in two different directions. Now, let's pretend that instead of being at the 60 mark, okay, let's pretend that it's at the 20 mark. Okay, so if I want to know what the electric field strength is at that 20 centimeter mark, okay, same thing. My electric field here is going in towards this, and my electric field at my positive is going out. All right, so now if you notice, these are both going to the left. So if they're both going in the same direction, then I'm going to add those two vectors or those two electric fields. Even though we have a negative and a positive, we have to look at where exactly we're measuring this to determine how they're affecting one another. Okay, so they're either working together like this, so we add them, or when it was here, they were working in the opposite direction, so we're working against each other. So in that case, we would subtract them. So this one here, we've got two-dimensional. So we have up and down and left and right. So we're going to look at those independently of each other. So if we look at the up and down, we've got 1 coulomb and 4 coulomb. Okay. So my 4 is bigger than my 1, so my net would be 3. So my net electric field would be in this direction, right? Because my 4 is bigger, and in this case, this is positive, so it's going away from that. Okay, and what I mean by this is this would have like a 1, the equivalent of 1 going in this direction. This would have the equivalent of 4 going in this direction, so my net would be 3 up. All right, so if we look left to right, in terms of our negative are going in towards the source charge. So this would have a 3 negative, and this would just have a 1 negative, right? And so my 3 negative is going to overpower, be more effective than my 1 negative, and so it's going to end up going in that direction. All right, so now to determine the actual direction, if something is pushing it up and something is pushing it to the left, then my resultant is going to go up to the left in that direction. All right. These ones here we will do conceptually. We're not going to actually calculate. However, this, as I said, is an example from your lab where you are going to calculate the two electric fields independently and then either add them together or subtract them. Okay. Now, forces, we can do the same thing. The difference is, notice my yellow dot here is now a charge. All right, so we can actually find the force using K, Q1, Q2 over R squared, but the idea is the same. The only added trick to that is you have to actually pay attention to the charge, the quantity of the charge. So this is a -2. So if this is a negative charge right here, okay, what would my positive do? My positive would be pulling it in this direction, and this is a positive, and it's going to pull in that direction. But since this is 3 plus versus only 1 plus, this one is going to kind of overpower, and my net result is going to be that force in that direction. And then once again, we could do our forces two-dimensionally as well. Okay, if my blue is negative, all right, my 2 red are positive. Okay, this positive is going to pull this in this direction. This is going to pull it in this direction. So if you're pulling something to the right and you're pulling it up at the same time, then your result is going to be in that direction. Now, we could do some trig and some fun stuff like that and actually determine that. We are not going to do that. These forces, we're just going to do conceptually on which direction they should go. Technically, this one should be a little bit closer to this one because this distance is closer, so it would have a little bit more of an effect. But I'm not looking for those actual specifics. I'm more looking at that general direction. So once again, this is kind of a odd one. We've got a negative here. So this Q, the 1Q is going to pull this in this direction. 3Q is going to pull it even more in this direction. Those distances are the same, but because this is 3 times bigger, it's probably going to go in that direction. There would be our resultant. So again, these ones here are going to be conceptually looking at that, but with our electric fields like this, we can figure out whether we add them or if they're going in the opposite directions, we can subtract them. All right, so there is electric fields.